In this video we're going to look at the concept of the rate equation, which is going to link rate to concentrations but in a mathematical form. So we're going to be linking the rate of reaction to the concentrations of each reactant. When we do this, we're going to be using the initial concentrations of the reactants rather than their concentration at any particular time. So we'll be linking rate to initial concentration, and the rate equation would have the form as expressed shown here. So what we would have is that the rate is equal to a constant K, which we're going to talk about in a little bit, multiplied by the concentration of reactant A to some power, to some indices, and then times that by the concentration of reactant B. So you can see that A and B were the reactants in this equation, and they're raised to some powers that we're going to talk about. Now, unlike equilibrium constant, they are not necessarily going to be the stoichiometry of the balance rate equation, so we just need to be a little bit more careful. We're going to consider what those powers are and how we find them out. So let's have a look at each term one at a time. So A in square brackets represents the initial concentration of A, and remember that concentration is measured in moles per decimetre cubed. Similarly, B is going to be the initial concentration of B in moles per decimetre cubed. And then we can look at M, and we see that M is a power, it's an indices, or an order. Well, you're going to use the term order in A-level chemistry. It might be a little bit old-fashioned to you, but you might have called these the indices at high school. The power at the top, and M is going to be the order with respect to the concentration of A. It's the power to which that concentration term is raised. So we've got the M being the power, the order with respect to the concentration of A, and N the order with respect to the concentration of B. And K is going to be our rate constant. So capital K in equilibrium was our equilibrium constant, but this is a lowercase k, and this is our rate constant. And the units of rate will depend, the units of the rate constant will depend on the orders. And we'll have to work them out. It will depend what those powers are. So the overall order is another term that we might come across, and that is just the sum of the orders. So if we've got M and M are the numbers 2 and number 1, then the sum of those would be 3. Now there is something to say about these orders that we'll come back to later, but these orders M and N are going to tell us about the number of moles of these reactants that are used up to and including something called the rate determining step. So we've got this step in our reaction that's going to determine how quickly or slowly our reaction happens, and the orders are going to give us the number of moles involved in this reaction up to and including that step. Now at A level, that step is often the first step to help us out, and therefore they're going to tell us about the first step of the reaction quite often. So let's just take a look at this and have a little play around with it. So we've got an example of a rate equation here. We can see that it says rate equals K times A in square brackets times B. Now there is no power written after A and B. That means that the power must be a 1. But it can't be a 0, because anything to the power 0 would disappear. It might be worth pausing the video now and typing in to your calculator a few different numbers, any numbers you like, and putting them to the power 0. So taking your calculator and trying out different powers, just putting in the numbers and then putting in 0 and seeing what happens. Now if you've done that, you should see that anything to the power 0 comes out to be the number 1, and therefore it wouldn't appear, because K times 1 would just be K, and so we'd ignore it. So if there is no power, then that power is a power 1. So we've got 1 for order for A, and WRT stands for with respect to A, and 1 for with respect to B. Now the overall order is the sum of those powers, so 1 add 1 is 2. Then we look at the next one, we can see that there's a squared after A, so the order for A is 2, but the order for B is 1. And if we add that up, then we get 3. And in this last one we can see that there's a squared after A, but there is no B, which means that B must have been 0 order, it wasn't there. No order, and therefore the sum of those is a 2. So what we're going to do now is we can take a minute to look at what the rate constant K is. It's just a proportionality constant. It's going to link rate to concentrations, and we know that the larger the value of K is, the faster the rate of the reaction is going to be, because we know that when we increase K, rate is also going to increase, therefore the larger the value of K, the faster the rate. Now the units of this are going to depend on our equation, so what we're going to do now is just a little bit of rearranging of equations and putting in units. Now when we just flick back a little bit, we know that rate, which we haven't written down here, but rate we know is always measured in, oops, sorry for that, I just did the wrong thing. Rate is always measured in moles per decimetre cubed per second. So we learnt that in our recap. So we go back. Now we're going to rearrange this rate equation. Rate equals K times A. So K is rate divided by, we're going to divide both sides by the concentration of A. So what we can do is we can work out the units for that. So over here, if we know that the units of rate are moles per decimetre cubed per second, and the units of concentration are moles per decimetre cubed, what we can see is that we can cancel those concentration units, and we'll be left with the units of K being seconds to the minus 1. So why don't you pause the video now and see if you can rearrange this second rate equation. So I've rearranged it to say rate, K is rate over A squared. Now starting to look at the units, and it's getting a little bit more tricky, and we need to use our indices rules. So remember that if we were using our indices rules here, then what we've got on the top line is just the top line, there's no brackets to expand, but on the bottom line we've got moles squared, because moles to the 1 squared is moles squared, dm to the minus 3 squared is dm to the minus 6. Now we've got to do some more rearranging. Look, we've got moles over moles squared, that's moles to the minus 1. And we've got dm to the minus 3 divided by dm to the minus 6, that becomes dm to the plus 3. And then we've got seconds to the minus 1. Now if you find that tricky, what you could do is you could think about this as being the units of concentration times seconds to the minus 1 over the units of concentration squared, which is then the units of concentration to the minus 1 times the units of seconds to the minus 1. So we've got moles to the minus 1 dm3, we're just changing the sign because it was c to the minus 1, and the seconds to the minus 1 carries forward. So pause the video again and have a go at the next example. So in this next example we've got rate over A squared times B, concentration of A squared times B, don't forget those square brackets, and I've had a look at breaking that down, and basically we've got one concentration term over 3, and then we've got our seconds to the minus 1. So actually we've got two more on the bottom line than the top line, so it's C to the minus 2, concentration to the minus 2. So we've got moles to the minus 2, because moles were to the 1, but we've got them to the minus 2, and then minus 3 becomes plus 6. So pause the video and have a go at this last example. And if you have a look at this last example, you can see that I got these units because I had the units of rate, which were a concentration per unit time, and then on the bottom I've got 4 lots of concentration. The overall order is 4, so I've got 4 lots of concentration, which means I've got concentration to the minus 3 times by seconds to the minus 1. Now every concentration is a moles per decimetre cubed. Now moles to the 1 becomes moles to the minus 3. dm to the minus 3 times minus 3 becomes dm to the 9, and seconds to the minus 1. Remember that every concentration is mole dm minus 3. So mole to the 1 to the minus 3 is mole minus 3. Mole dm to the minus 3 to the minus 3 is dm to the plus 9. We haven't done anything with the seconds to the minus 1. So that's the end of this short video on the idea of the rate equation. Over the rest of this pack we'll be building up lots more information on this rate equation.